including the NASA Infrared Telescope Facility, so looking in the near and mid-infrared, the Canada-France-Hawaii Telescope, and the Keck Observatory. Fabulous instruments and producing wonderful science to this day. We've also sent some very expensive telescopes into space, and if people thought that those ground-based facilities were expensive, these things get really expensive, such as the Compton Gamma Ray Observatory, the Hubble Space Telescope. That one got more expensive because it had astigmatism, and they had misfigured the mirror, and we had to create new instruments to go up to help correct that. Chandra X-ray Observatory, Spitzer Space Telescope in the infrared, International Ultraviolet Explorer, and the Orbiting Astronomical Observatory 2, reaching way back to 1968. In 1970, I was at Cape Canaveral when Orbiting Astronomical Observatory 2B was launched. Unfortunately, the fairing, the part of the rocket that covers it while it's going through the atmosphere didn't come off. And so instead of looking at the sky, it took a sample of the Indian Ocean. We're sending more things out, and I'm going to talk about this one more a little bit later. This is the James Webb Space Telescope, mid-infrared to far infrared, a huge aperture, 8-meter aperture, that's going to be in space at the L2 point. I'll point that out a little bit later. There are certain things that you just can't do from Earth's surface. You have to get away from Earth, and notably you have to get above Earth's atmosphere to be able to do it. Interplanetary spacecraft can do some of that work. Things that you can go to, oh, they're great for that. And they often use telescopes to do their work. Now, they use other instruments too, but there aren't too many spacecraft that say go to Saturn, go to the outer solar system anywhere without a telescope or some kind of camera on board. As an example, the OSIRIS-REx mission, which not too long ago, I guess a little less than a year ago, arrived at what was originally called asteroid Bennu. Now we're not too sure if it's an asteroid or a comet, but it's using a telescope to map the surface. Now the shape that's shown there was the best shape that we could glean from observations with ground-based telescopes. And you'll see in the next slide, no, they didn't do too bad a job with that. However, the texture of the surface was completely unexpected. So you had to go there and be close enough to see essentially clouds on the surface to see what that surface texture was like, and it was indeed a surprise. Another surprise, and this is a Japanese mission, the Hayabusa mission, that went to the asteroid Itokawa. Now notice the shape of the spacecraft. It's essentially a box with an antenna on it, and it's got two rectangular solar arrays hanging off the sides of it. Well, here's asteroid Itokawa, and there's the shadow of the spacecraft. That surface was also completely unexpected. They hadn't done quite as good a job at getting the shape of this one. The shape, as it turns out, is another of these things. We've seen a lot of these with our space missions. Things turn out to be bilobed. It looks like they're two things that came together. And often they describe them as looking like bowling pins. Well, somebody was a little bit too enthusiastic when they were bowling with this one. They bent it. Cassini at Saturn got some just amazing images from its telescopes. It had a narrow angle telescope and a wide angle telescope. This is the moon Enceladus. Enceladus is just that little black dot there. The rest of this is material being spewed out of the south pole of Enceladus into space from a liquid water ocean underneath an ice crust. There are cracks at the south pole that are spewing this stuff into space, and some of the particulate matter, coming out of there, go out and form the E-ring at Saturn. Linda's going to be talking some more about this later. This is what Enceladus looks like if you try to look from Earth. This is a Cassini image, but those particles that are coming out of the South Pole are extremely small, and kind of like if you have a dirty windshield and you drive into the sun, that windshield is just glaring at you. But if you turn around 180 degrees, you can see out of it just fine. Those little bitty particles tend to scatter light just small angles. So you see that scattered light from back here, you can't see it from what we call backscatter. Well, this, we're looking at backscatter and you just don't see those plumes. But if you look in forward scatter, they really show up. And if you get an even a little bit closer view of it and a little bit higher resolution, better time resolution, you can see even more structure in those plumes. That's mostly water. Linda will tell you a little more about that later. What's in addition to the water makes the astrobiologist say, "What? I want to go back there. I want to go back there." Voyagers 1 and 2 that Linda and I both worked on. This is something of an old slide. You'll see here it shows them in between what's called a termination shock. This is all solar wind flowing out. That's where it hits a shock and slows down. So this is still sun material. Well, both of them have crossed this heliopause. They're now in interstellar space. They're not in the part of space that's dominated by the solar system, except for gravity. They're out in interstellar material now. They're sampling the interstellar medium. They're seeing things that you just can't see with a telescope on the ground. You have to send a spacecraft there to measure those. But you can't send spacecraft everywhere. If you want to do something with Alpha Centauri, yeah, it's the nearest star. Even in kind of science fiction dreaming spacecraft building, it would take us 40 years to get there. But there are a lot of people saying, well, the design that would do that can't possibly work with our current technology. With our current technology, it would take 40,000 years to get there. So it's not something we're going to do with spacecraft. So if you're going to use telescopes instead of spacecraft, why would you put a big, really expensive telescope in the Earth space, in Earth orbit, or at one of the Lagrange points? Well, people often say, well, it's the ceiling. The atmosphere really distorts things. And yeah, getting above it does help, but ground-based adaptive optics, which people here in Canada are working at some of the cutting edge of adaptive optics. For instance, on the 30-meter telescope that's being built in Hawaii, 30-meter diameter mirror. Those things work very well, and they're much less expensive than sending something into orbit. Here's an example. This is Neptune, and you just barely see Triton down there, as you would see it through about a 2-meter aperture antenna. This is the same thing as seen from an 8-meter aperture antenna, and you're starting to resolve clouds here just a little bit. You can tell that it's more than one cloud, and Triton shows up a little better down here. Then you turn on adaptive optics, and you see this. You can see the equatorial cool spot in Neptune, 2 completely distinct cloud systems, and maybe even a little third one there, and another one up in the northern hemisphere. And Triton has come down almost to a point. Those adaptive optics work very well. They give you almost as good resolution as you can get from space. They can correct for optic sag. This is one of the problems they have with large telescopes. If you zenith point a primary mirror, it might have a shape like this, and my hand wasn't really steady, so that looks kind of wavy, but that's supposed to be a nice parabola. If you tilt it on its side and support it at those 3 points, what happens to the mirror, and I'm showing the actual shape as tilted. Here's what the shape was before it was tilted. That sag has distorted the mirror, and so it's out of focus now. Adaptive optics can correct that. So we owe a lot to adaptive optics. There are also some techniques, and amateurs have been using this as well as professional astronomers, taking time resolve, very quick images. Those images taken when the seeing just happened to be perfect, they throw away everything else. The ones that were good, they stack on top of each other to improve the signal-to-noise ratio. The image I'm about to show you is Jupiter, taken by an amateur with a 14-inch telescope. That looks like a Hubble image. That's by Damien Peach from England. There's another fellow, Anthony Wesley in Australia, that does work like this also. It's amazing what they're doing with very small telescopes. So it appears, well, spatial resolution is not a good reason to send a telescope in space. You can spend less money and essentially get as good a resolution as you could with a space telescope. But there's another thing having to do with scintillation in the atmosphere, and that's not spatial resolution, that's the intensity of the signal that you're seeing. How bright is the signal? So I'm drawing a chart here. This is intensity, and this is time. So if you're looking at something like a well-behaved star, there are no star spots, there are no flares, there are no oscillations in the star. The amount of intensity that you see is rock steady with time. It's a flat, straight line all the way across there. Okay, if you start looking through the atmosphere with uncorrected optics, what you measure looks something more like this. It's twinkling, getting brighter, getting dimmer, and so on. If you turn on adaptive optics, it doesn't twinkle nearly as much. It's better than a factor of 10 improvement, but it's still a little bit. Now, unfortunately, if you're doing certain experiments, like you're trying to watch the transit of an exoplanet in front of its star, the signal you're looking for is something like this. Here in green is the signal. It's right on top of the yellow. And here it drops, and I've actually exaggerated this by almost a factor of 5. It drops a tiny bit when the planet goes in front of the star and then goes back up. If you put that adaptive optics signal on top of that and try to pull this signal, the green signal, out of that, no, that's not going to work. So the need for accurate photometry is one of the reasons that you would want to send a telescope into space. So we've got one good reason there. Let's continue. Another thing that can happen in our atmosphere is that certain wavelengths of light can get absorbed out by that atmosphere. This is called opacity. And we have a diagram here going from very short wavelengths. This is essentially gamma rays over here, down to X-rays, visible, infrared, mid-infrared, far infrared, shortwave radio, long-wave radio. And then on top of that, some of the things that we do with it: gamma rays, X-rays, and ultraviolet, atomic and molecular electron transitions, for say, taking an oxygen molecule, hitting it with an ultraviolet photon, you can break it apart, and that involves an electron transition. That photon gets absorbed. Well, that with ozone transitions, carbon dioxide transitions, everything from about there up gets absorbed out. None of it gets down to the surface. Up here in the near infrared and mid infrared, molecules can vibrate, and these are kind of odd. If I'm a carbon dioxide molecule, here are 2 oxygens, my head is the carbon. They can vibrate like this, or they can vibrate like this, and they absorb photons in that range, which overlaps with molecular rotation transitions. And I'm not going to try to demonstrate rotations. I don't want to fall over while I'm up here. But they overlap somewhat and provide some of this opacity that absorbs the photons that are coming in. They never make it to the surface. And then on the far side, down here, all of these electrons getting ejected from their atoms up in the ionosphere cause the ionosphere to be electrically conductive. And that's like shielding Earth with a big sheet of metal. Nothing's going to get through it. So even with a long wavelength radio, nothing gets down to the surface, so we can't see it there. So the need to see a spectral range that gets blocked by our atmosphere is a second good reason to put a telescope in space. The final thing, I'm going to give you 3 good reasons here. The third reason, Earth rotates. It has night and day. And if you're trying to, for instance, that chart that I showed where you're trying to watch a transit of a planet in front of its star, that's easy to do at night maybe with adaptive optics, really good adaptive optics. But in the daytime, that's not going to happen. You're looking at something, and my example here is You're looking for a transit of a planet in front of its star, and this can last from less than an hour to maybe a few hours. But you don't know when it's going to happen, and it could be days in between transits, it could be weeks, it could be months or years in between transits. You just don't know beforehand. So you're having to watch that star continuously until you see that dip. So the need for long duration, continuous observation is another reason to put telescopes in space. So there are three good reasons: the long duration observations, spectral, and the photometry. Now, a little bit about how we do this. The typical telescope light path, there's a barrel, there's a primary mirror, and I'm just going to show a Schmidt-Cassegrain for right now. A secondary mirror, light comes in, reflects off of that primary to the secondary and to a focal plane and back behind there for the Schmidt-Cassegrain. Now, there are multiple things you can do. You can put a lens there, as most amateurs do, and just take a look through it with your eyes. Or you can put a focal plane sensor there, which might be something like this. Now, I'm showing a focal plane array here that is 10 by 10, so there's 100 elements there. The typical ones nowadays have millions of elements, so this is a great under-exaggeration of what one of these things is. But the idea is each one of those little squares is a pixel. Each one of those pixels, when light comes in and strikes it, the light causes the electrons to be kicked off of some of the semiconductor there and start being able to just move around inside that pixel. It's a free electron. The more photons come in, the more electrons get released. The electrons over a period of time accumulate in that pixel. You can call it a light bucket. And after a while, you block the light so it's no longer going in. There's a certain number of electrons in there that tells you how many photons and therefore how bright was the light coming in. Those are sent to electronics that measure how many electrons were in there. They convert that to a digital signal, and then with radio, send that down to Earth. So you have all of those pixels which can generate an image, and you can measure how bright each one of those pixels were and make all kinds of scientific deductions from that variation in brightness with spatial. People do infrared, X-ray, and gamma ray mirrors for space telescopes, and they are different from their optical counterparts. For instance, the infrared mirrors, the mirror coatings that we use for optical telescopes, and that's usually aluminum, well, it doesn't work very well for especially the long mid-wave infrared and the far infrared. So they use beryllium instead, which works much better. They're pretty much like optical telescope mirrors, but it's a different coating. So there's not a whole lot of difference there. But you get the X-ray and gamma ray mirrors, it's a completely different kettle of fish. X-rays and gamma rays don't reflect well from any material. They'll go right into a metal, whatever metal you want to use, beryllium, aluminum, iron, whatever. The X-rays and gamma rays will penetrate unless it's just a grazing incidence reflection, and then they reflect fairly well. So this brings us to the idea of grazing incidence mirrors. What's a grazing incidence mirror? Well, looking into the front end of one, it would look kind of like that, and you turn it 45 degrees. It's almost a cylinder, but one end is slightly smaller than the other. You turn it 90 degrees, and from the side, it looks kind of like that. Now those top and bottom edges are actually slightly curved. They're not quite straight. But this thing is like a cylinder, smaller at one end than the other. So you put one of those things somewhere, send some light in, and when the light hits the surface, it reflects and comes to a focus some distance downrange from there. Now, looking in the front of that, at the top on the left side, there's not much aperture there, so you're not collecting many gamma ray or X-ray photons. So if you want to collect more photons, get more aperture out of it, you put more concentric mirrors. So these things are all put concentric, one inside another. They all focus at the same point. So if you're looking at an X-ray or an ultraviolet or gamma ray telescope, what you'll probably see is a very long, skinny barrel. And if you look from this end, you'll see a bunch of these things, so you'll see a bunch of concentric circles. Well, here's Chandra X-ray telescope. There's that long, skinny barrel, and there are those concentric circles. They're using Grazing incidence mirrors. Some of the future missions we've got flying. Well, James Webb is coming up pretty soon here. I think they're saying 2021 now for that launch. They've had a lot of trouble with getting this thing ready for flight, and the main trouble has been it's large enough that you can't fit it inside a rocket. You have to do some things. You have to fold things, you have to fold up things, and that means once it's in space, you have to deploy these things. Well, the deployment has been a headache. This has always been a headache with spacecraft. Every spacecraft project manager chews on his fingers every time a deployment is necessary. Well, there are lots of deployments with this thing, especially, with this sunshade here. Since it's looking in the infrared, you want that to be nice and cool. Well, you need to shade it from the sun with these things. These are very thin plastic with a metallized coating on them, and they have had trouble in the past when in their test, you deploy them and something tears them. Well, they don't work too well when they're torn. So they've been working on that problem for quite a bit of time and have spent some money on that. Plato is another going out for looking for exoplanets and also looking at stellar oscillations. So it's going out to this L2 point that I mentioned before. Here's Earth and the Moon. L2 is a point out here where the gravities of Earth and Sun combine, that if you put something there, it pretty much stays there. You might make a halo orbit around that point, but it'll pretty much stay there. It's nice and stable, and if you're looking outward, Earth and the Moon are never in your field of view. This is one of those cases where you're doing very accurate photometry. Another one, Cheops, this is ESA led. It's looking not just at exoplanets, but the satellites of exoplanets. So things much smaller even than the exoplanets. And that means you need exquisitely good photometric measurements. And so it's going out into space to do those very high accuracy photometric measurements. We've got others going up, just recently started as a project, the Wide Field Infrared Survey Telescope. So infrared, this is long wavelength and mid wavelength infrared, doesn't get through Earth's atmosphere. The International X-ray Observatory, again, X-rays don't get through Earth's atmosphere. So we're sending all these things out there to make measurements in places that we couldn't measure before. And as usual, we'll find things that, well, some of them maybe we predicted and we'll verify those, but we'll also find things we never expected, such as maybe something like this. This was actually a t-shirt that Linda had, and I wish I had one of those, but I don't. For those of you who are familiar with Monty Python, and now for something completely different, I'm going to go off of the astronomy side for just a second. This is something I've been designing for the past 2 years. It's a rotating space station. These things are not space shuttles. It's not that big. Here's a 100-meter bar down here. Those are Dream Chasers made by the Sierra Nevada Corporation. You can put 7 people in it. Those are our lifeboats. If you're going to have something that will hold as many people as a cruise ship up there, you're going to have a lot of things that are going to look like cruise ships, like having a way of getting off if there's big problems. For a scale, there's the inverse. So it's pretty big. It's a lot bigger than the International Space Station that's up now. However, the contrast in size from the previous space station, the Skylab and Mir space stations, to the International Space Station is larger than the jump from the International Space Station to this. So it's not that big of an extrapolation. Now, this is an engineering drawing that I did. I don't have fancy 3D rendering software and so on. I just have this boring stuff that can do engineering drawings. But we have an interior architect working with our team that does have the 3D, and he can turn this thing into that. We're expecting, well, this distance here is about 200 meters. It's a little short of 200 meters. We're expecting to put 400 people on board this thing. It rotates, so we can put lunar G in these habitation modules around here, and we can extend these two elevator shafts, if it proves to be successful, can extend those shafts and put habitations out there and get Mars G to see how humans and crops and whatever else would do, both at lunar G and Mars G. We're expecting first rotation in 2025, and first tourists to go up. We'll have about 200 spaces for tourists in 2027, if we get the proper funding profile. We've never heard of anybody not getting the proper funding profile, right? And there's another big if, and Cameron's shirt has one of our hopes on it here. If SpaceX and Blue Origin come through with their promise of very large, very inexpensive launches to Earth orbit, they're talking about being able to launch 100 metric tons to Earth orbit for something on the order of $40 million. Elon Musk a year and a half ago said $7 million, but that's it. Nothing has to be refurbished. NASA says 130 metric tons with their rocket for $1.3 billion. I know which one of those I'd buy. I'll take 3 or 4 questions now, and then we'll go on to Linda. And if there are more questions after Linda's finished, we can do some more. Thank you.
Thanks very much, Tom. Does anybody have some questions now? We could hold them and ask them at the end. We've got plenty of time here in the room, so keep that in mind. So, Linda, you want to get set up here? So, Linda started her career. She went to university in California and got her PhD from UCLA, and then went to work at the Jet Propulsion Lab. And she's worked on many projects, including the Voyager project and the Cassini project. And I just wanted to say something about Voyager, if you don't remember. In 1964, a NASA engineer figured out that all of the planets were in a perfect alignment to go and have a very economical grand tour of the other solar system. And so that resulted in the Voyager program. Well, a similar thing happened in the lower mainland and Victoria area with our RASC meetings. We have had a grand alignment of our RASC meetings. Our meeting here in Victoria Center is Wednesday, Vancouver's Thursday, and the Sunshine Coast is Friday. So we were able to pool our resources together to bring Tom and Linda out here for this talk. So it's kind of a neat opportunity, and I don't think we've done that before. So this is very much like a Voyager thing. So let Linda take it on.
So good evening, thank you very much. And I'd like to share with you some of Cassini's intriguing discoveries, in particular some new discoveries in just looking at those data. First, just a little bit about myself and a little bit about Cassini. I've actually worked on Cassini for over 30 years. And when I first started working on Cassini, my oldest daughter, Jennifer, had just started kindergarten. And now she's married with a daughter of her own. And so that just shows the amount of time that can pass so quickly with some of these missions. And in so many ways, by studying the Saturn system for 13 years, Cassini truly revolutionized our understanding of the planet, the ring system, the beautiful moons that are there, and the giant magnetosphere. But before I get started, I want to talk a little bit about something about how astronomy smiles on this new friendship that we have. And so here's some pictures of Reg and Tom, and here we have lunch together, and then the two of us. So we're really very happy and pleased to be here and to share our knowledge with you. This shows an overview of the Cassini mission. It's shown against the 30-year orbital period of Saturn. So it takes Saturn 30 years to orbit the Sun a single time. So I basically worked on Cassini for one Saturn year. The idea for Cassini was born in the 1990s. The instruments were selected, and NASA started to build the spacecraft. We launched in 1997, and then spent 7 years on our journey to Saturn. On our way, we flew by Venus twice, then the Earth, and then Jupiter with gravity assist. You can think of a giant slingshot. You borrow a little bit of energy from each planet and continue on out to Saturn. So we arrived at Saturn in 2004. This is a few years past the northern winter solstice. We had a 4-year prime mission, and the spacecraft was healthy. The science returned incredible, so NASA approved a 2-year equinox mission. That's when the rings are edge on to the sun. I'm a ring scientist, and what a fascinating time to be at Saturn, to look at the rings with the sun just edge on. Then a 7-year solstice mission, ending just after northern summer solstice. And at the very end, a series of proximal, or what we call grand finale orbits. We bring the spacecraft very close to Saturn's rings, then in a single orbit, jump over the rings, fly between the gap between the rings and the planet for 22 orbits, in a place where no one had flown before, with some remarkable new science, and I'll talk a little bit about that toward the end of the talk. Well, how big is Saturn anyway? Here's the Earth and the Moon to scale, as is the distance between them. Now, if we add Saturn and the rings to this picture, you can see that Saturn truly is a gas giant. Second largest planet in our solar system, 10 times further away from the sun than the Earth. And if you could turn Earth into a marble, 764 Earths would fit inside Saturn. So truly a gas giant, made mostly of hydrogen and helium, star stuff. Just didn't get big enough to turn into a star. Now here's an overview of the Cassini 13-year mission. What it shows across the top are what some of the orbits look like. These are Titan flybys. Saturn's giant moon Titan, about the size of the planet Mercury. As we flew close to Titan, we could change the shape of the orbit, change its inclination, its eccentricity, and its direction. So we call Titan our tour engine. It's like having a huge additional fuel tank on board Cassini to shape our orbits. 23 flybys of Enceladus. We originally had 3 in the prime mission, but it was so interesting that we added 20 more over the course of the mission. 15 more close flybys of some of the other icy moons of Saturn. Here to show you the seasonal change in the northern hemisphere across the Cassini mission. Now here's what Cassini's orbits look like. Almost like a ball of yarn. You can see there the grayish orbits are early on, down to the bright green orbits, which are the orbits near the end of the mission. And each of these is shaped by flybys with the moon Titan. Here's NASA's Cassini orbiter and the European Space Agency's Huygens probe. You can see people for scale here. The Cassini spacecraft is about 7 meters tall, and this is a 4-meter high-gain antenna we use to send the signal back to the Earth. This is the Huygens probe. Here's another view of it. The Huygens probe parachuted into the atmosphere of Saturn's moon Titan and soft landed on the surface. So two very exciting missions. And over the course of these missions, I would take my daughters to see Cassini being built. And on one occasion, here I am with my younger daughter, Jessica, and this is just before they buttoned up Cassini and sent her down to the Cape. So Jess kind of very proudly, dressed up and covered so we wouldn't get any dust near Cassini, in very close to the spacecraft. One of the things that we watched over the 13 years of the mission is we watched the seasons change on Saturn. An incredible surprise for Cassini was to notice that when we first got there, that the atmosphere in the northern hemisphere, the hemisphere you don't see from the Earth, was actually blue. Blue, very reminiscent of the bluish color of Neptune. It turns out that hemisphere with no sunlight or little sunlight falling on it because it's shadowed by the rings. Those hazy golden particles fall out of the atmosphere because they're generated by interaction with the UV solar photons, and you basically are seeing some of the methane in the atmosphere. This is equinox, and I'll talk a little bit more about that. And then finally, this is the southern hemisphere of Saturn. You can see the ring shadow almost like a giant sundial, moving from one hemisphere to the other as the seasons change on Saturn. Here's the Cassini Spacecraft and the suite of instruments. We have optical remote sensing instruments, everything from the short ultraviolet into the mid-infrared. We actually use the high gain antenna for microwave remote sensing, both for radio science and looking at radar wavelengths, and then a suite of fields and particles instruments on the spacecraft. So here's the remote sensing palette. You can see the two telescopes here for the cameras. Fields and particles instruments here, a long magnetometer boom, and here's the edge of the Huygens probe. Now you'll notice there are no solar panels on board Cassini. At 10 times further from the sun than the Earth, you'd have to have solar panels the size of tennis courts. It would be very hard to fly a spacecraft with solar panels that large. So instead, what you have is 3 radioisotope thermoelectric generators. We use the decay of plutonium and the heat from that decay, turning the heat into electricity to power the spacecraft. It doesn't take a lot of power to run Cassini, but those generators then lasted for the duration of the mission. A little bit about some of the science. This is one of the views with the rings edge on at equinox. This is a mosaic that we put together. We had to brighten the rings by a factor of 30 so you could see them in this picture. We brightened them up by a factor of 60 and they're still very, very faint on this side. The only illumination for the rings is the reflected light coming from the planet hitting the rings. Basically, you've turned off the sun to the ring particles unless you're a big ring particle. If you're big enough, you stick up above or below the ring plane. The rings on average are only about 10 meters thick. And if you're a big particle, then you would catch the rays of the sun as you stick above the ring plane. So one of the things we did is we turned our cameras to look across the rings to see where the places might be where there's 3-dimensional structure. This is one of my favorite pictures. If I go back here, we looked in particular along the edge of this V-ring here. This is the Cassini division. And what we saw is we saw shadows. Shadows 1 to 3 kilometers long. You can see evidence of some of those biggest particles. You can imagine like giant icebergs, maybe half a kilometer or a kilometer, in a sea of particles only 10 meters thick, sticking up and casting shadows in the rings. And so in a few places, this was one that was most striking. We actually saw shadows and knew that large particles were there crowded together at the outer edge of the V-ring. Now Saturn's rings have very simple names, starting in close to the planet, D. This is the C ring. The bright B ring has the most material Cassini division. The name of our mission, and named after the astronomer who discovered that gap in the rings. There's the Encke gap, a tiny gap here, the Keeler gap, and here's the A ring. So this is the beautiful structure of the rings. Now a lot of that structure has a similarity to spiral galaxies. The same physics, the same ideas work. Imagine taking a spiral galaxy and wrapping it up very tightly so the arms pass by one another. And you get something called a spiral density wave. This is your galaxy wrapped up very tightly, starting here, getting tighter and tighter and tighter as you go across the ring. And these waves are throughout the rings. They're basically a sensor into the rings, telling us something about the density of particles by how the waves stand out as they go across the rings. They're driven by resonances with the moons. This is a 2-to-1 resonance. The moon Janus goes around 1 time for exactly 2 times for ring particles where the resonance is launched. This is kind of like a wake of a boat going out. Very beautiful. And sometimes there are glitches in between because Janus shares an orbit with another moon of Prometheus. Every once in a while, every 4 years, they change places. And so the wave changes its pattern just a little bit. We think the rings might be very young. At the end of the mission, Cassini measured the amount of material in the rings. It wasn't as much as we were expecting. So we think the rings might only be 10 million years old, maybe 100 million years old. maybe Saturn's rings formed at the time of the dinosaurs. So perhaps the early dinosaur astronomers looked up and said, wait a second, where did those come from? And there were Saturn's rings. Another one of my very favorite pictures, Tom showed this at the end of his talk. This is a unique, very unique view of Saturn, and of Saturn's rings in particular. This is a solar eclipse image. Saturn is covering up the sun, and so we could pull our cameras in very close and make this mosaic. And so you can see this is the E-ring that Tom talked about coming from Enceladus. You can see the rings themselves. The ring material is actually putting light onto the night side of Saturn. And the sunlight is refracting around the edges of Saturn. So this white ring is every sunrise and sunset on Saturn at the very same time. So just a very, very beautiful image. And if you look carefully, there are some more planets in this image. You have Mars, Venus, and the Earth and Moon. And we actually spent time taking pictures of the Earth and Moon in particular. We spent 20 minutes, so you can see here's the Earth and here's the Moon. And we knew we would be taking these pictures, and so we asked people to go out and wave at Saturn. And you could be in the picture. We took into account the speed of light to get the photons out to Saturn. Go out and wave at Saturn, and you'll be in the picture. So how many people in this room went out and waved at Saturn? Yeah. So, and then we said, send us your, take pictures of yourself waving at Saturn, and send them to us. We got pictures of families, we got pictures, people holding up their dog paws, people holding up their babies to wave, clubs, lots of astronomy clubs, school classes, going out to wave at Saturn. So we took these selfies from around the world, basically from the west coast of the United States all the way across Europe. You were in view to go out and wave at Saturn. We took all those selfies, we recreated that image of Saturn. And in fact, this was very popular. People wanted to go and find themselves in this particular image. So you could go, and I did too. I went hunting for Tom and I in this particular image. So that was really a lot of fun. I got people interested in wanting to know more about what was happening. And so there's the picture again. Oop, I think we're over. Okay, finally wrong. Okay, this is another picture of the ring. It's a tiny gap. This is the Keeler gap in the outermost region. Turns out it has a moon inside of it. This moon Daphnis right here is actually creating and opening up this gap. And it's creating this beautiful wave along the edge of the ring. There's another wave going off this direction. And this is basically very much like a boat wave. As the particles go by Daphnis, they go a little bit faster, and they create this wave. And you'll notice this picture looks kind of grainy. That is real. It turns out that the ring particles tend to clump together, and we're actually seeing all kinds of evidence of clumping in this image getting very, very close to the rings near the end of the mission. So the particles stick together, they make these long clumps. They don't last probably very long. They kind of break apart and reform and break apart and reform. And that clumping is present throughout the ring. And it's more obvious in some places than in other places. We're not sure why, what's going on. Lots of questions coming from this picture. If you look up even more closely at Daphnis, it's actually pulled a little tendril and ring particles off the edge. You kind of see this wave going here, tendril and ring particles. It sort of looks like it has a ridge. It's accumulating ring particles around it because they're so close. Atlas is another moon that's very close to the rings. Right near the outermost ring, the A ring, you can see a central, what we call parent body or central shard, and then this huge skirt or disk of ring particles looking very, very fluffy and very porous moon, very interesting. And here's another set of moons. This is Atlas in color. Here's Daphnis, another moon, Pan. These moons are all to scale. Pan is opening up the Yankee Gap. So very unusual looking moons. A little bit about this moon, Titan. This is what Titan looks like in the visible. It's basically a nitrogen-rich atmosphere, but instead of oxygen like the Earth, it has methane. And that methane gets hit by sunlight at the top, broken apart, and forms longer and longer hydrocarbon chains or smog. So basically, you're looking at the hydrocarbons like a smoggy day on Titan, and that's what the atmosphere looks like all the time. And so this is what we saw with Voyager. So we wanted to go back and see the surface. And so that's why we carried the Huygens probe. Go through the haze, get to the surface, and see what it looked like. It was really incredible. So Cassini released the Huygens probe, did a little bit of a maneuver so we didn't follow Huygens into Titan. And then Cassini flew overhead as Huygens parachuted down to the surface. Took it about 2.5 hours to reach the surface, and then soft landed. When we built Huygens, we didn't know if we'd be landing in a sea of liquid methane. We didn't know what the surface looked like, but fortunately we landed, and I'll show you, this is the movie in the final 10 kilometers of Huygens coming down toward the surface of Titan. We noticed what looked like sand dunes, we noticed what looked like river channels flowing on Titan. It was just really amazing to see these very, very first pictures come back in January of 2005. So we landed on the surface. We landed in a dry stream bed. We saw rounded icy pebbles that could only be rounded by flowing liquid going by. And it turns out that the methane is just at the right temperature on Titan to look like water. Methane can form clouds, methane rains down to the surface, flows through river channels into lakes and seas. And so Titan, much colder than the Earth, is remarkably Earth-like in many, many of its characteristics. And here's another view of that same picture. We carried a lamp on board. We knew the spectrum, the color of that light, so we could get a true color for the surface of Titan. And here's the horizon, the atmosphere. And just here's for the moon. Here's a footprint of an astronaut. Here's the astronaut in the flag, just to give you the perspective looking toward the horizon here on Titan. And here are some of those dendritic river channels coming down to this dry lake bed. Here's a view of Titan. You can see some of the clouds that are present over some of the seas on Titan. Here's another view. You can tell from a specular reflection that it was liquid on the surface. And here's one of those methane clouds. Here's a better view. The lakes tend to be mostly lakes and seas of the North Pole. This is the giant seas tend to be in this location, and here on this portion are the lakes. This is just missing data. This is from radar data, piercing through the haze and bouncing a signal back to Cassini. This is a view of Ligeia Mare, about 1.5 times larger than Lake Superior, and it's very obvious to see the river channels flowing into it. It's about 100 meters deep of liquid methane. Here's a better view of these tiny little lakes over on this other side, tens or hundreds of meters across. On the very last flyby of Titan, we actually got radar data across the lake region. And what we found was really incredible. The lakes are actually up higher by about 100 meters, and they have these rims around them. And here's an artist's concept of what one of those lakes might look like with the rims around them. And we think what might happen is that earlier Titan was colder, and as Titan warmed up, the nitrogen came through the surface, blew out these pits, gave the rims, and then it just rained down and filled up these little tiny lakes. There are no river channels flowing into the lake, so it's very different, very, very different, very close together on the same world. And this is very recent. This paper came out just a couple of weeks ago. Finally, I want to talk about Enceladus. Enceladus is a tiny moon. I just showed for scale. This is the Earth, the moon, and here's the size of Enceladus. So it's really quite small. It's only about 500 kilometers in diameter. Here are those 4 distinct bluish fractures with the geysers coming out of it. And I was looking for something that was about the same size as Enceladus, and you know what? Vancouver is 460 kilometers across. So it's almost the same size as Enceladus. So there it is. Here's another view, again in forward scatter. Now you can start to see the individual little jets coming out. And what we found is that the jets had not only water and water ice, but also lots of different carbon fragments in there. larger parent molecules are broken apart. There's been a number of papers, one just came out a week ago, talking about fragments, maybe they're fragments perhaps of amino acids, or pieces that could become amino acids. And here's a spectrum of some of the organics, which you're just looking at here. It's color-coded based on the mass of, and this is just the amount basically that's there. Here's the water, the methane, red is carbon dioxide. You've got C2 organics, C3, C4, C6, on out. Longer and longer chain organics. There's an ocean. These are all coming from the liquid water ocean. It's salty. And it turns out that there's hydrothermal vents on the surface. And what we know that they're there is there's an excess of hydrogen coming out. And in particular, sort of the smoking gun is there's tiny particles of silica, nanosilica. And this material can only grow in water very close to the boiling point. That tells us there has to be someplace on Enceladus where water is very close to the boiling point. We think that's hydrothermal vents on the seafloor here of Enceladus. Now we have hydrothermal vents here on the Earth. In this particular set, it's called white smokers. They're also black smokers. They're very deep in the ocean. There's no sunlight. It's at very high pressure. Often at places where the Earth's crust is being pulled apart. And what you see is it's teeming with life. We have little crabs and tube worms, little islands of life feeding off of the nutrients coming out of these hydrothermal vents, using the heat energy to sustain the life. So we wonder, could there perhaps be life in this ocean on Enceladus? It's very intriguing. We didn't quite have the instruments to make the measurements for the big, long-chain hydrocarbons. We didn't have a little microscope to see if we could see anything moving around in the water. But we'd like to go back with those kinds of instruments, perhaps land on Enceladus, and see if we might be able to find life. That would be amazing. Some of the unique findings for the grand finale included a new radiation belt. We got the mass of Saturn's core very accurately, 15 to 18 Earth masses. The atmosphere is rotating down to about 9,000 kilometers, differentially rotating. We think the atmosphere compresses, the hydrogen becomes actually metallic, almost fluid-like, and that's where we start to generate the magnetic field. The magnetic field axis and the spin axis of the planet are almost perfectly aligned. Only planet in the solar system. Everybody else, Earth, Jupiter, Uranus, Neptune, all have tilted axes. Complex organics are coming from the rings, and tiny grains coming from the rings. That's very intriguing. Also, there's particles that are falling out along magnetic field lines. We call it ring rain, that they get charged up and fall through. Newly detected atmospheric currents connect the atmosphere and the rings together, and then the rings are much younger than we expected. So just a whole host of new discoveries in those final 22 orbits. And then finally, it was September 15th, and Cassini had been running out of fuel. We knew we didn't want to accidentally, once out of fuel, crash into Enceladus. Titan is a liquid water ocean, and could there be life in methane seas? We don't know. So, to be careful, we basically flew by Titan for a final time. Titan nudged us in towards Saturn, and the spacecraft hurried up, going into Saturn, going very, very quickly. And it was really a very interesting day. I had my daughters, Jessica and Jennifer, there, and there's my granddaughter, Audrey, at her first big spacecraft activity for the end of the Cassini mission. And now I want to show you a movie that we put together with some of the highlights, some of which you've seen here tonight, about the Cassini mission.
A lone explorer on a mission to reveal the grandeur of Saturn, its rings and moons. After 20 years in space, NASA's Cassini Spacecraft was running out of fuel. And so, to protect the moons of Saturn that could have conditions suitable for life, a spectacular end was planned for this long-lived traveler from Earth. In 2004, following a 7-year journey through the solar system, Cassini arrived at Saturn. The spacecraft carried a passenger, the European Huygens probe, the first human-made object to land on a world in the distant outer solar system. For over a decade, Cassini shared the wonders of Saturn and its family of icy moons, taking us to astounding worlds where methane rivers run to a methane sea, where jets of ice and gas are blasting material into space from a liquid water ocean that might harbor the ingredients for life. And Saturn, a giant world ruled by raging storms and delicate harmonies of gravity. But before its work was done, Cassini had one last daring assignment. Cassini's grand finale was a brand new adventure. 22 dives through the space between Saturn and its rings. As it repeatedly braved this unexplored region, Cassini found new insights about the origins of the rings and the nature of the planet's interior, closer to Saturn than ever before. On the final orbit, Cassini plunged into Saturn, fighting to keep its antenna pointed at Earth as it transmitted its farewell. Until, in the skies of Saturn, its journey ended, with Cassini becoming part of the planet itself.
Truly a great mission. And I look at that and I say, I want to go back. Already. And it turns out that we do have a mission to go back, that we found so much unique science that NASA recently picked a mission, a New Frontiers mission named Dragonfly. And that mission will go back with an octocopter to land on the surface of Titan in multiple places and make measurements. It even includes instruments that could look for evidence of complex hydrocarbons and the possibility for perhaps very unusual life, basically to fly around Titan. And I'd love to go back with a similar mission, kind of mission to Enceladus, to land there and continue the work that Cassini has started. With that, I'd be happy to take questions. Thank you very much.
Excellent presentation. Thank you so much. Could you speculate on the origin of the ring? You talked about the grand finale being one of the questions for grand finale tried out.
Yeah, the question was, what about the origin of the rings? If they're really young, where do they come from? We think perhaps a comet or maybe a moon of Saturn got very close, was torn apart by Saturn's gravity. So there are ideas about it would take something like some kind of a rare event. Although Saturn's rings are mostly water ice, so that's an interesting part of the puzzle as well. We get rings that are mostly water ice.
Are the small moons accumulating material, or are they giving off material in the rings?
Good question. Are the moons accumulating material or giving off material? A little bit. They can accumulate material only up to what they call the Roche load, and then it can't stick to it any longer. And some of the smaller moons further away actually lose material. Particles hit them, they're bombarded, and they actually have rings of material. There's some of the very tiniest moons that lose their material with time.
It's such a significant role that you played. What's your favorite moment or your most amazing moment of the mission?
I really liked Saturn orbit insertion. because we did the burn and got safely into orbit around Saturn. Then we turned our cameras around to look back at the rings at a much higher resolution than ever before. And I'd worked on Voyager in the 1980s, and I felt like I'd waited a long time to go back and see what the rings might look like. So that certainly for me was memorable. Huygens probe landing also was phenomenal. How about you? What were your favorite ones?
Surviving launch.
Considering the differential rotation of the rings, how long they will last?
With the differential rotation of the rings, how long will they last? We've actually done some calculations based on how much the rain and the particles are falling into the planet. And some estimates are like maybe only another 300 million years. The edges of the rings are held in place by resonances with moons, so they don't expand outward any further at the moment. But based on how quickly they're losing material, estimates are perhaps a few 100 million years.
With all the shortages of plutonium-238 over the years and other missions, I've always wanted to ask the people in Cassini, how did you get 7 kilograms of this stuff?
Yeah, I think we were just lucky that they had that amount ready for us to go for a major mission. And being a joint mission with the European Space Agency helped. There was actually one point where Congress wanted to cancel Cassini, and the Europeans wrote a letter to the head of over the United States, very high level in NASA, and said, wait a second, we spent all our money on our side, you can't cancel it now. And it worked.
One of the things that Cassini was able to benefit from is that the United States, in the years leading up to Cassini, was operating a nuclear reactor, the Savannah River nuclear reactor, which was not a water-moderated reactor. It was a graphite-moderated reactor, which is very efficient at making plutonium-238. Now, 238 is not like plutonium-239 that they put in bombs. 238 is not fissile, so you can't make a bomb out of it, but you can make these radioisotope thermoelectric generators out of them. Now, the one problem with the graphite-moderated reactors, Chernobyl was a graphite-moderated reactor. And with graphite-moderated reactor, if something goes wrong and it loses all its cooling, it keeps running. With a water-moderated reactor, when they lose their cooling and lose their water, the reaction stops. Now, they still stay hot because of radioactive material that's left over, but not nearly as much heat is being generated as a full power running reactor. But the graphite moderated reactors are very dangerous in that respect. And the United States decided to quit operating the 2 reactors that it was operating, the one at Savannah River, which was making plutonium-238 for civilian uses, and the one in Hanford, Washington. Both of those have been shut down for decades now. And so the amount of plutonium being generated for radioisotope thermoelectric generators is much smaller than it was before. Back then, yeah, 72 kilograms for Cassini, you've got it. Now, 7.2 kilograms, oh, we're going to have to save up for a decade to get that. So it's a very different situation now.
Although I'll point out, Dragonfly does have a radioisotope thermoelectric generator on board it as well for power. So it will fly with radioactive material.
I have one question for each of you. Linda, how likely is an ice drill mission to Enceladus? And then for Tom, I heard on a podcast a wild idea of sending a collector, a light collector of some kind out to, say, just past Pluto and using the sun as a lens of the light bending around the sun to grab as a gravity lens, which would give us potentially kilometer scale resolution on Alpha Centauri system. Have you heard anything about that, or ideas or thoughts?
Well, the ice drill on Enceladus, I think it's a cool idea. In fact, I'm working on a couple of concepts. One of them would use radioisotope heat to melt through the crust and go down that way. And the second one is a spacecraft that looks like a snake, counter-rotating cylinders. It looks like it's called eels, and it's supposed to spiral its way down through one of those cracks down to the ocean. So we're looking at concepts to go through the icy crust of what we call ocean worlds. There's Enceladus and Europa and maybe Dione and other worlds too. So we're trying to do that, yes.
For the second question, you're asking about the gravity lens focus. And it turns out the farther you get from the sun, the further that Einstein ring gets from the sun. So you start seeing a ring of light from whatever's back behind the sun. If you're closer than 550 AU, the Einstein ring is within the sun, so you can't see anything. So Pluto, at its farthest, gets around 50 AU out. You have to get 10 times, or actually 11 times further than that, to even start to be able to see an Einstein ring. And so you have to go a long way in a big hurry. Voyager's been traveling, what now, about 42 years? And the farthest from Voyager 1 is at about 140 AU. So you'd have to go almost 4 times that far to even start thinking about doing an Einstein ring around the sun. It'll be a while.
Cool idea though.
Can you talk about the new discovery of the 20 new moons of Saturn?
Oh, I saw that. 20 new moons. Saturn now has the record for having the most moons of any planet in the solar system. And it was basically from Earth-based observing to look basically at quite a distance from Saturn. There's a ring of debris in a sense that maybe a large object broke apart. Some of it's retrograde, going backwards from the rotation of the other moons. Some of it's, I think 17 are retrograde, a few prograde, but very recently announced, so it's 20 new moons all at once. Wow. There's a question.
Just one quick comment and then a question to follow. And for yourselves to be able to have an extended career doing such wonderful work, it must be sometimes wonderful beyond words for you. And for all of us, I think, in this room that have interest in those sort of things, what an extraordinary time to be alive when these things are being discovered. Things we can look back on 25 years ago and now, viewing things so differently in some ways.
Right, yeah, I feel lucky to have actually lived through, the Apollo era, all like the wonderful things, going into space for the first time, all the way out, through Voyager. I worked on Voyager and now Cassini. It's just, is amazing. You had a question as well?
I did. I don't know if this requires an extended answer, but I think sometimes when we view the interface between science and government, the gap in scientific literacy that you must encounter must pose some special problems. And the people that you interface with, are they more of an engaged sort?
For the talks, I think that both of us give is for a range from elementary school classrooms, college age, just public variety of talks to try and get the public excited. And one of the things that really got them excited, something simple, the Wave at Saturn campaign. We had so many hits on our website to learn more about Saturn and understand the Cassini mission. So it's trying to make those connections, and it can be tricky.
Certainly one of the problems that we have in communicating with the U.S. government is that the people who hold the purse strings are not necessarily scientifically literate. And some of the experiments that we want to do are fundamental, but they're very complex. And trying to explain one of these experiments to somebody with no background in science at all of the problems they've ever dealt with had units of dollars or full-time equivalent employees. That's all they understood. And it's really difficult to say, well, we're expecting 6 watts per square centimeter per steradian out of this, and if they start thinking about, okay, what was I going to do for lunch?
It's the first batch who originally discovered the hexagon on top of Saturn, and then hasn't been involved in any of this stuff for the last 30 years. Have you found anything more out about that?
The questions about the hexagon at the North Pole of Saturn, I had so much I could have talked about. It's a 6-sided jet stream at the North Pole of Saturn. It's about 2 Earth diameters across. First discovered in the 1980s by Voyager. It's still there. It still rotates at the same rate. It still has 6 sides, and it's still a mystery. We don't know what sustains a 6-sided. It's the only one in the solar system where it actually, usually a jet stream has rounded edges and circular. South Pole, it's everything circular. Only the North Pole of Saturn has a hexagon at the North Pole.
I just wanted to mention something. I was running out of time, so I skipped this during my talk. One of the things about my space station that would be of interest to astronomers is that becomes a base for building things in zero G. You wouldn't build things right there at the space station. It's rotating so that people don't get the illnesses that you get from long durations in zero G. You can go over and build something in zero G, go back to that space station and spend your weekends and so on there recovering. But if you can build in zero G, people have heard about things like the TMT, the 30-meter telescope. This would be by far the largest thing we've ever built. But that's built down here on the ground in 1G. Once we get that space station built and start a space construction industry, imagine the HMRT, the 100-meter radius telescope. This is a 200-meter diameter mirror that you're in zero G. None of these forces that bother you in 1G can prevent you from doing the alignments and so on. You put this thing together in space so you don't have to put it into a rocket that's only 5 meters across or 9 meters across. You can build it fully deployed. I mentioned that with the James Webb Telescope, one of the big problems facing such missions is deployment. No deployments here. You build it completely constructed, fully aligned, and fully calibrated in orbit, and then with electric engines, gently nudge it to where you want it to be, like the L2 point or something. 200-meter telescope? Yeah, we can do that.
Any other questions?
Just a couple of things. Linda mentioned that your career is kind of one Saturnian year. And I just retweeted something the other day, just pure coincidence, that Hubble has been in space for one Saturnian year and has observations from all those different things. So that's out there. And I was going to ask Tom a question. The station you're proposing, who is going to build it? Who is going to run it? Is it NASA or kind of private sector or a mishmash or what?
On September 3rd of this year, and then finally culminated on October 1st of this year, the company Orbital Assembly Corporation was incorporated in California in the United States. I'm the vice president of Orbital Assembly. We're going to do the construction. We have ideas for the machines that we're going to need to do that construction. Our first project here on the ground, once we get a little bit of funding, is to build a demonstrator for one of those machines that will build the structural backbone of that spacecraft, of that space station. And it's completely privately funded. This is not going to NASA. NASA should love this. NASA has found that they built the space station and then they were chained to it. They have to pay for the operations year after year. Now, of course, there are other countries kicking in money, but the burden of that goes to NASA. The greatest part of the burden goes to NASA. And so they have been chained to this expenditure every year to keep that going. We would do this space station as a private venture for tourists to go to, for companies to lease research space, for national space programs like NASA, like the Canadian Space Agency, like the Australian Space Agency, ESA, can go up and say, we need 24 months of a laboratory this size, we're going to need some water, we need this much electricity. They can rent it for those 24 months and then get out without having to pay for all the operations.
Are you taking reservations yet?
Not yet, but if you Google Gateway Foundation, you can get to a website where the Gateway Foundation is the umbrella organization over Orbital Assembly. And there's a group called The Crew that our CEO started this, John Blinko started this. You can join The Crew. Don't remember how much it is. I think it's maybe $5 a year or something like that. We're actually going to start hiring from The Crew, and we've already started doing that. The interior architect that did our 3D renderings, we hired him from out of The Crew. we've started that, and from the crew, once we get the things rotating and have it ready for tourists to go up, it's essentially a lottery, but 2 of the crew will be sent up free of charge.
What did you do for the 7 years waiting for Cassini to arrive at Saturn?
Okay, what did we do for the 7 years? You think, oh, that's a long time. Well, it turns out that we hadn't developed the software to fly the spacecraft beyond pointing at an RA deck. And so we developed the rest of the software. And for the 4 years of the prime mission, we designed every minute of that 4 years of what science we would take. Typically, we take science for, say, 18 hours and then point at the Earth and send the data back. And notice that all the instruments are on board Cassini, kind of like a giant Christmas tree. So you have to turn the whole spacecraft whenever you want to look at something, and then turn the antenna toward Earth to send the data back. So we spent 7 years planning and thinking and actually thinking ahead to what the next part of the mission could look like.
I'll add to that a little bit, working on the engineering side while the early part of the flight was going on. Imagine that you have a stick shift car, but this stick shift car doesn't have all of its features put in. So you've got one steering wheel for each of the 4 wheels. You've got one stick shifter for each of the 4 wheels. You have a little machine up on the front that instead of having a breaker for the points of the car, this is an old standard ignition system, there's something that you have to keep tapping to give you a spark plug. Things were very rudimentary when we first launched, and so there was a lot of work involved in getting the spacecraft to do very simple things.
And I think the reason for that is NASA does something in order to try and make the budget more even. They threw over the fence the development of the software, and so that's why we ended up putting that money and everything. It costs a lot to build the hardware, so we threw over the fence the cost of the computer, the computers to operate Cassini. Cassini had to be very smart. If you figure a one-way lifetime of an hour and a half, you don't command by command work on this spacecraft. We'd send up 10 weeks of commands, sequential commands. Every single camera shutter, every single observation, when to point at the Earth, and made Cassini smart enough to be able to handle some situations that it might have to handle. And if it ran into problems, which it did once in a while, it would basically sort of shut everything down, and you can imagine it sort of curl up and go, help, help. And then, we communicate with it and figure out what was wrong and get it started up. But that only happened a couple of times. We were very lucky, very, very healthy spacecraft.
A question for Tom. Did you ever meet Gerardo O'Neill during your time at NASA, and was he an influence to the Gateway Foundation?
No, some of the things that he did are slight influence, but if you look at the designs for his cylinders, they're dynamically unstable. If you take a cylinder like that with water in it and start rotating along its long axis, depending on the size, within a few minutes to a few days, it'll be rotating end over end. And so we knew we were going to need to do something completely different from that. But the attention to human aspects, what do humans need not just to survive, but to thrive in a situation like that, some of those ideas we have carried forward. Cameron.
Sort of two-part question. The size of your teams, so with Cassini, during the slowest times when things were either starting out or sort of mid-mission, like how big was the team, how big did the team get, and what were those teams like size-wise compared to the Voyager missions?
The teams on Cassini, I think, were quite a bit larger than the Voyager mission. We had a slightly different model, where each of the science teams actually commanded and operated their own instrument versus having a central location like JPL, which is what we had for Voyager. A typical team would have maybe 10 to 30 people per science team. There's 12 instruments on the teams. At JPL, probably at its maximum in building the spacecraft, we're probably about 300 or 400 people. Now we're down to, I think, 4 of us probably, 2 days a week or something.
Question. Uranus and Jupiter even has rings too, right? Are they ice rings like Saturn?
Question is, Uranus and Jupiter, do they have rings too? It turns out that all of the giant planets, Jupiter, Saturn, Uranus, and Neptune, all have rings. Only Saturn has water ice rings.
Okay.
Jupiter, Uranus, Neptune, their rings are rocky material, not icy materials. Jupiter's ring is very fine-grained particles kicked off of some of the moons, in particular from Amalthea, Himalaya. Uranus has 9 very narrow rings, and Neptune's ring is very unusual. It has 3 thick ring arcs and then a very tenuous ring of material. So Saturn by far is the most massive. And we think the only
those
water
are
ice ring.
probably part that they would be from different events that may have, like, would have happened to those planets that would be maybe different, like comets versus.
Right, what created the rings, say, around some of
Things
these
like
other
that,
planets? Well, Jupiter, we know, once those tiny moons are gone, the very diffuse rings of Jupiter will be gone. Uranus and Neptune, we wonder, could we be looking at, maybe if you have a youthful ring, say it's Saturn, as the rings age, you end up with, say, like the 9 narrow rings around Uranus, something like that. Another thing is that there's some objects out there, smaller objects like asteroids or objects further away that actually have rings of their own. Triclo is an example, and we're really Chiron, that places that have rings of their own. So these smaller bodies, which is intriguing too.
One of the interesting things about the Uranian rings, especially one of the rings, the epsilon ring, is that it's darker than charcoal. Charcoal is what, 8% of the light falling when it gets reflected. Its albedo is 8%. The epsilon ring looks like it's about 4%. So it's extremely dark stuff. It may be that it's very old and there were some carbon materials in with water that over a much longer period than Saturn's rings, those carbon materials exposed to radiation, like cosmic radiation, were changed into longer carbon and nitrogen and oxygen compounds that turn very dark.
Any other questions?
Okay, well, thank you so much. What an extraordinary, successful mission, so congratulations on that. What a wonderful example of the best that we can be. Is that? Well, their primary mission was to visit Vancouver, and I want to thank Linda and Tom for extending their mission and coming over to Victoria. So this was really great. While they were here, James Francesco kindly took them up to the Dominion Astrophysical Observatory and gave them a tour of the Plaskett telescope, named after John Stanley Plaskett, I guess the man who made it all happen, and he's been celebrated by having a telescope named after him. And he's been celebrated with plaques up on the wall, and pictures here and there. But for the 100th anniversary, the Canadian astronomical community said that the finest tribute that we could give John Stanley Plaskett was to put his image on a beer bottle. So for that, the Moon Underwater Brewery came up with a thing called Plaskett's Big Dipper. DIPA stands for double IPA. And as a tribute of appreciation we have for each of you a glass with that on there. So now, I've had discussions with Tom. He doesn't really like IPAs, but I can assure you that I have sampled numerous types of beers and they all taste excellent. These things.
Reg, the glass is empty.
We'll have to see what we can do about that. Well, thank you very much again. Remember that we are going up to the 4th floor of the Astronomy Lounge for tea, coffee, and further questions. If anybody is here who's new to RASC and would be interested in finding out more, please come back down to see me. I'll give you my business card, which has got our RASC website on it for Victoria, and you can continue your journey. Yes, Lori?
And also on the 5th floor of this building, there's a lovely little telescope that is being used this evening by the students from the physics department.
Till 10 o'clock.
Until 10 o'clock. So please go and visit up on the 5th.
Thank you very much.